and in today's presentation, I'll be talking about the recent project which I was involved in at DeepSense AI, where we were working on the problem of multi-object tracking of people in surveillance videos. In the talk, I will describe our objectives, our problems we had, the solution we came up with, and the conclusions of our research. So let me briefly introduce myself. I work as a data scientist at DeepSense AI, where I have a chance to apply a variety of AI methods to the problems from the fields of computer vision and NLP. In particular, today I will be describing the project on multi-object tracking. At the same time, I'm a PhD student at the Warsaw University of Technology. My past academic background is in automatic speech recognition, but currently I'm focusing more on chatbots and dialogue systems. At DeepSense AI, we are a team of data science experts. We turn our expertise into AI-powered solutions for our clients. We are a team consisting of data scientists, data engineers, software developers, DevOps engineers, and business-oriented managers. We have a proven track record of more than 50 commercial AI projects in multiple branches of industry. We work for companies from all over the world, both for large companies and for smaller ones like startups. We also conducted some R&D projects, including the ones in cooperation with Intel and Google Brain on reinforcement learning and generative adversarial networks. As a team, we guarantee the world-class skills in computer vision, NLP, and predictive modeling. Let's move to the main part of the presentation, and let me briefly introduce you to the topic. So our objective in the project was to develop a proof of concept system for tracking people who are in a shopping situation, in a shopping environment, and they are being recorded by a so-called CCTV camera, or actually multiple CCTV cameras, also known as surveillance cameras. These people are moving around the shop. They are looking at the objects on the shelves. Some of them are waiting in the queue, while others are shop workers like cashiers. So this example here is quite a crowded shop, a small one but full of people who we would like to be able to follow in their movements. So let me rephrase and define the problem of multi-object tracking, often abbreviated as MOT. It can be seen as comprising of the two steps, first one being the object detection. So we want to find objects of interest in a single image, in a single video frame, which means we want to predict their position, their location, and draw also bounding boxes around them. In our case, the objects were people. They were of class person, but in general, the object can be of any kind. Once we already have detections for a given video frame, we want to assign them to so-called tracks. A track is an abstract term which represents the same object across multiple frames of the video. And based on some defined distance metric, we want to assign the detections to tracks. Let's move to the overview of existing tracking algorithms. The ones which I will be describing belong to a specific class, the specific paradigm of tracking called tracking by detection. This is quite a modern approach which works well thanks to the advances in object detection itself. So first, the first algorithm which I would like to cover is called SORT, although it has nothing to do with sorting. It's just an acronym that stands for Simple Online and Real-Time Tracking. It was introduced in 2016 by Bewley et al., and it was designed to be targeted towards online and real-time tracking, which means that the tracker only considers the previous and the current frame when doing the assignment. And it was designed to be as simple as possible, rather than trying to cover all the possible corner cases. It ignored, for example, visual information of the inside of the bounding boxes. And the detection to track assignment relied completely on the intersection over union of bounding boxes. For object detection in the original paper, they were using faster RCNN architecture. Maybe it's not the point of this presentation, so I will not go into much detail about faster RCNN. But another very important element of the tracking algorithm in SORT was usage of Kalman filter framework for motion estimation. I have a separate slide for Kalman filters, so wait for it. For the assignment of detections to tracks, they used a Hungarian algorithm, which is a minimum cost assignment algorithm based on a cost matrix, and in this case, the matrix was based on IOU values. Let's move to the already mentioned Kalman filter. This is actually one of the most widely used estimation algorithms, and you can understand estimation quite broadly here. This is an algorithm that operates in a loop, which consists of two steps, predict and update steps. First of all, it produces estimates of hidden variables based on some measurements. And then, based on the past estimations, it provides a prediction of the future system state. So in order to use the Kalman filter framework for your estimation problem, you have to define at least two things. The first one being the system state, which is a vector of the target parameters that you want to model. And the other one is the dynamic model, which is a set of equations describing the dynamics of your system, which means the relationship between the input and the output. A very good explanation of the Kalman filter framework can be found under the link which I provided on the slide. When applying the Kalman filter framework to motion estimation in MOT, it's typical to estimate the state, to model the state as an 8-dimensional vector, where two coordinates represent the bounding box center position, another coordinate represents the height of the bounding box, and the fourth one is for the aspect ratio. The following four are the first derivatives of the first four parameters. And there is one state vector for each tracked object. A very important assumption that is used in this framework, used, for example, in SORT and the following algorithms as well, is the assumption of constant velocity motion. As you can see on the animation, it may be fine for tracking pedestrians because approximately they are moving with a constant velocity on a straight line. They follow a straight line, but maybe it's not necessarily the optimal choice for describing the dynamics of people moving around in a shopping scenario. But as I said, this was a proof of concept project. So for this phase, we just sticked to the constant velocity motion model as well. During the detection to track association step, this state estimate is used when calculating the distance between the track and the detection, and the track is represented by the bounding box, that is the estimation, the estimate of the state in the next frame. The next year, in 2017, an extension of SORT was introduced, and it was called DeepSORT. It was actually the same group of researchers who just extended their original SORT algorithm with visual information. So now the association metric combined both motion information and appearance. By appearance, I mean visual features, which were embedding vectors obtained from a convolutional neural network that was trained with a classification objective for classifying people. And its goal was to learn to extract some visual representations of bounding boxes. These representations were vectors extracted from the penultimate layer of the network. According to the authors, this should result with better handling of occlusions, which are the situations when one person is being covered or hidden behind another person. When their trajectories cross each other, this should result with less identity switches. So that's the reason behind adding this visual information as well. And another concept introduced in DeepSORT was a gallery, which is let's say a list of the past, the history of these embeddings for each track, which are kept for a fixed number of frames and then forgotten. And when doing the assignment, the nearest neighbor match is performed between the gallery, between the features kept in the gallery and the ones extracted from the new video frame. Another algorithm is quite brand new. It's from this year. It's called FairMOT. It's different, slightly different compared to the previous ones because it has a single model which combines the two tasks of object detection and the extraction of visual embeddings. So object detection and re-identification are in a single model. Therefore, it's called one-shot tracker as opposed to the two-step methods described before. It still relies on the Kalman filter framework, and according to several MOT benchmarks, it's the current state-of-the-art algorithm. If we already have our system and want to evaluate its performance, its quality, we have actually quite a lot of metrics to choose from. There are more than 20 of them defined in the benchmarks, so I have not listed all of them on the slide, just selected the most important ones, being the MOT accuracy, MOT precision, and identification F1, respectively. The MOT accuracy is the measure of how well the tracker detects objects and keeps their trajectories independent of the precision with which the objects are located. Their locations are estimated, in contrast to MOTP precision, which is the measure of error of estimated position for the pairs of objects and hypotheses. This is quite counterintuitive, but although it's called the precision, the lower the value, the better. And IDF1 is basically an F1 score measure for how well our model performs in terms of re-identifying the same person across multiple video frames. And these metrics are implemented, for example, in this PyMOT metrics library module. It's very useful. It was very useful to take it instead of implementing from scratch because it's it doesn't really make sense to reinvent the wheel in this case. So let's move to our particular scenario, our case study. So as I already mentioned, we wanted to track people who are moving in a shopping environment, who are moving around the shop. We also wanted to add support for simultaneous tracking across several cameras mounted in the same shop. If a person moves from one camera to another, he or she should still be tracked. Another problem we wanted to tackle was to create a 2D map visualization to represent the people's motion, not only with bounding boxes, but also with markers on a 2D map on the bird's eye view of the shop. And last but not least, we wanted to detect actions performed by the moving customers, moving people, who we came up with 3 actions, being walking around the shop, waiting in a queue or paying, and being rather a cashier than a customer, respectively. So now let me talk about the data. We did an extensive research on the data sets. Before starting the project, we found quite a lot of data sets to choose from for all the components of the pipeline, for person tracking, for re-identification specifically, and for action detection too. So it seemed there is quite a lot of choice. But on the bad side, we came up with the conclusion that actually none of these available data sets was perfectly matching our needs, because some of them were of too low resolution, like the caviar dataset, which is quite old already. Other datasets were recorded under different conditions in different environments, like corridors or offices, while others were about tracking pedestrians who have for sure different walking patterns than people who are shopping. So what we did instead, as we stated that it was not easy to find the representative data for the problem, we, for the POC project at least, decided to use footage from CCTV cameras that we found on YouTube, one of them being the crowded shop sequence, which I've shown you in the beginning of the presentation, and another 3 videos coming from some scene that we named multi-camera shop. This was the same scene shown from different cameras mounted in the same shop, and the videos were almost synchronized. So it seemed to finally match our needs, but there was one problem. The data was unlabeled, unannotated. So we found CVAT, which is the computer vision annotation toolkit, part of the open source OpenCV library. We used CVAT for manual labeling of bounding boxes, tracks, and actions with some semi-automatic labels, automatic labels obtained with the object detection for bounding boxes, but then we had to label the tracks and actions manually. So this slide shows what I mentioned and what we named the multi-camera shop sequence. As you can see in the first few seconds, there is a guy who's wearing some yellow shorts. He disappears behind the shelf to reappear once again on the rightmost camera after a while. Then a lady enters the shop from the outside. She disappears behind the shelf. Another gentleman enters. They meet inside. She goes to the cash desk. After some seconds or after a minute almost, our yellow short friend reappears at the cash desk with Coke and newspaper. Another person enters the shop, and so on. In total, the sequence is 95 seconds long. So, as I mentioned during the overview of existing algorithms, one of them was DeepSORT and another was FairMOT. We experimented with both and didn't really see any significant differences in terms of performance on our data on the multi-camera shop sequence, and we decided to stick with DeepSORT as our, let's say, starting point for the code base, which we customized because DeepSORT's code was much cleaner and much easier to customize than FairMOT. We coined a new name for our algorithm, for our custom version of DeepSORT, a very witty and funny one, DeepSense-Sort. So for object detection, we used YOLO v3 network here, as it's supposed to be faster, more suited for real-time applications than, for example, region-based approaches like faster RCNN. So we trained the network on the crowded shop sequence plus carefully selected subset of the multi-camera shop sequence. We made sure that no person was present in both the training and validation subset of the data in the multi-camera shop. We also added some more features to DeepSense-Sort. We added the possibility to predefine areas in each camera, for each camera, where new tracks may appear, because without this feature, we were noticing a lot of false positive new tracks being initialized in the middle, out of nowhere, in the middle of the shop. So we only wanted to let them appear next to the entrance or exit or by the camera borders. We also added support for multiple cameras tracking, which means we were also having a purely visual comparison without this Kalman filter framework for those detections and tracks that were not matched with Kalman filter and embeddings to match objects across multiple cameras. And also we added information about the 2D coordinates of each bounding box as additional information, additional component of the association metric. I will say a few more words about these 2D coordinates in a while. It has not yet been covered. For re-identification, this was the component that we were most unsatisfied with. The original DeepSORT embeddings didn't really work when a person moved from one camera to another, or disappeared behind the shelf and reappeared, but facing in a different direction. It could not really recognize it's the same person that it was a moment ago. We experimented a lot with different extractors, different features like ORB, LOMO, also applied these FairMOT embeddings to DeepSense-Sort tracker, but nothing really satisfied us in this dimension. So another component was this action detection component. So for each tracked person, we wanted to tell the model to tell us what he or she is doing. We had 3 classes, which were, as I mentioned, walking around the shop, waiting in a queue or paying at the cash desk, or not being a customer, but a cashier. For this purpose, we used the decision tree classifier with some feature engineering using features based on X and Y position, the between frame translations along X and Y axis, proximity to other objects, other people, and also proximity to the predefined position of the cash desk. We achieved satisfactory results, which you can see as the numbers at the bottom of the slide. For the problem of creating a 2D coordinate visualization, a map, we used a so-called homography transformation, as we wanted to mark each detected person's position on the map as a marker. This is a transformation that transforms each pixel from one plane to another, these planes being the floor surface seen from the camera and the same floor seen from the bird's eye view on the 2D map. So this required estimating the transformation matrix, the homography matrix, and this transformation, this calculation of this matrix requires mapping between at least 4 pairs of corresponding points in these 2 images. So we had to manually point pairs of points of pixels that correspond to each other on the floor or any other characteristic spots in the picture. So for each camera, we separately pre-calculated the transformation matrix that transformed the image from the camera to the same global coordinate system for the 2D map, and therefore we had the combined map for the 3 cameras together. You can find the detailed explanation in under the link which I provided for the homography transformation calculation and so on. Highly recommended. Very interesting topic. So the next slide will be about the experiments and the results, the outcome of our pipeline. So I'll put the full screen here because it's not well seen, if not full screen. You can see the tracking, the bounding boxes, keeping the color, meaning the same ID is assigned to the track, which works quite well when the person is within the same camera or is still visible in the scene. But unfortunately, as I mentioned, we were not able to keep these IDs after a person entered the shop. Immediately she changed the ID that was assigned to her. Same will happen after she comes back. This lady, this blonde lady, comes back from behind the shelf. On the right side of the video, you can see the mentioned mapping, the visualization of the markers of people's position. These were calculated using this homography matrix by transforming the coordinates of the center of the bottom edge of the bounding box, which is more or less supposed to represent the feet position of a person. These are being projected onto the bird's eye view floor in the 2D coordinates. Yeah, so this is it about the visual, let's say, aspect of the pipeline results. Let me explain why I put no numbers for camera 1, the external one. We have decided not to label the people who have not who do not enter the shop at all. So it introduced a lot of noise into the detection and tracking, and therefore it makes no sense to present the metrics here. But for the camera 2 and 3, we labeled everyone present in the video, so the metrics are quite representative and quite satisfactory when looking at each camera separately. So to sum up the presentation, what we did was we developed a proof of concept multi-object tracking system which worked well enough. We were satisfied with the quality of object detection, single camera object tracking, 2D coordinates mapping, and action detection. But the most problematic component, which did not work well enough, was the re-identification in case when a person moves from one camera to another, or when the same person reappears within the same camera after being hidden for a while and then is seen from a different angle, from a different view. We have several ideas to try to improve the pipeline, which we have not tried yet. First of all, we would like to take advantage of some human parsing models to detect some key points, some masks for body parts and clothes, but this could potentially limit this real-time possibilities of application of this pipeline. So we have not tried it yet. We could also try different approaches to re-identification, use some, for example, some Siamese networks. For the multi-camera tracking, we should probably allow to merge tracks, or to assign the same track ID to two detections or more detections seen simultaneously in multiple cameras if a person is visible from different cameras at the same time. For motion estimation, an idea for improvement could be to get rid of this constant velocity assumption and try some more complex motion model. There is a lot of space for improvement still, but for us this was a very interesting research topic and the proof of concept project. This is all for now. Thank you for your attention. And if you have any questions, feel free to ask them during the conference or contact me later via email.
All right. Thanks, Arthur, for the presentation.
Hello, everyone. Let's confirm if you can hear me well.
Yes, we can hear you.
Perfect.
Okay. Thanks for the presentation once again. We have some questions. Maybe let's start with the question from Kamil. You mentioned a few metrics. Are they the most important for this type of problem? Why did you choose these metrics, not the other out of 20? Because you mentioned there are over 20 metrics you can use.
Yes, as it was mentioned during the presentation, in the papers on the problem of multi-object tracking, you can find results in terms of around 20 metrics, and I think I consider the ones which I put on the slide the most, let's say, representative ones. If you don't want to get overwhelmed with numbers, they just provide like a general impression of how well your model performs, because the other ones, like I can describe as, let's say, components of these, of some subcomponents of these metrics. So this, as it was on the slide, let me have a look on the slide. This MOT accuracy represents the ability of your model, of your system, to keep track of the detection and assignment of detections to tracks. Then MOT precision is about how precise your model is in terms of locating the bounding boxes, how close they are to the ground truth. And IDF1 is a selected representative metric for re-identification, and others include, for example, the number of identity switches, number of false positive detections, and so on. So they are, like, as I said, subcomponents that also are reflected in the more general metrics, which are the three on the slide.
Mm-hmm. I don't have a lot of experience with object tracking, so I've got a follow-up question on how do you get, or where do you get the benchmark, the right bounding boxes to measure the performance of your bounding boxes, your model generated?
Okay, so if I understand the question correctly, it's about where do we get the labels from, so the ground truth information. As I said also in the presentation, we found a very useful tool called CVAT, Computer Vision Annotation Toolkit, and we used it to annotate the data for object tracking and also for this action detection Fortunately, the current state of the art in object detection is so good that you can at least try to produce some of the labels. You can treat some of the predictions of some pre-trained object detection models as labels, and then just fix the ones that you consider wrong, or add some other new ones manually. So this is what we did. We ran object detection prediction with some model, which is also included in this CVAT toolkit. With just clicking a button, it applies object detection to your data, and then internally we had to label the track IDs for each frame, for each bounding box, add some bounding boxes manually, and also label the actions performed by each person in each video frame. So this was quite time consuming. I would say around 20 hours to label these 4 short 2-minute sequences. So yeah, it took us 20 hours to label, to generate labels for 8 minutes of video.
Cool. That's the answer I want to hear. Okay, and could you say simply a little bit more on detecting actions of the customer? You mentioned paying. Could you say a bit more on that? Did you use 2D floor map to detect the actions, or something else?
As I said, the model which we came up with, and it was working well enough, was based on a decision tree and some features that we came up with, like proximity to other objects, the position of the bounding box in the current frame, the translation in the position between 2 consecutive frames, and also the proximity to the cache desk, for example, for detecting the action of waiting in a queue. It was quite easy to detect it because of being close to the cache desk. We had to first define for each camera which contained the cache desk where this cache desk is located, and then we could use these features, feed a decision tree with them, and the predictions were quite okay.
Okay. Did you use 2D mapping to do how far from, for example, cache desk the object is, or 3D?
To be honest, I don't remember what was the final feature. I think could have been 2D. Would make more sense.
Okay, cool. Okay, you mentioned improvement ideas. Are you going to continue with the project?
Well, for sure, we see that there is a business need for this kind of systems. So we have some customer who's potentially interested in this topic. So this is actually why we started working on this in this direction. And there is a quite high chance that this will be continued as a, let's say, real project.
Cool. Okay, Artur, thank you very much for the presentation.